Here we're going to talk about phase diagrams. So phase diagrams, they describe the different states and state changes that occur at various temperature and pressure conditions. So the prior representation that we had just seen was just showing various temperatures and showing phase transitions, but all at the exact same pressure. This will be able to vary both the pressure and the temperature. So the different regions on this particular diagram will represent individual states. And there's going to be lines that represent the state changes, those phase changes. So liquid and gas line is the vapor pressure curve. And both states exist simultaneously at those lines. And critical point is the farthest point on the vapor pressure curve. Beyond that, you get that supercritical fluid. And there's a triple point in the temperature pressure conditions where all three states exist simultaneously. This sounds very bizarre, and you can look up some YouTube videos about a substance at its triple point. And it's really fascinating. The substance will pretty rapidly transition between liquid, gas, and solid, and so that means you're not hitting the triple point exactly. You're kind of dancing around it, but it's more of a theoretical value than something that you can exactly pinpoint, exactly hit. But yeah, it's pretty fascinating to see that. And so for most substances, the freezing point increases as pressure increases. So we'll see what these look like here. So this is what one of these looks like, the phase diagram for water. So here on the pressure side, you have 760 torr, which is 1 atmosphere, and it's saying it's not to scale, so it's just in general. This is what's going on. So here we have pressure, and here we have temperature. Again, not to scale, but water we know. So here, this is solid, this is liquid, this is gas. This is the critical point, so kind of above these conditions, you have a supercritical fluid, which we had briefly talked about, but this is high temperature, high pressure. And so these lines represent phase transition. So as I'm going across here, I would transition from a solid to a gas, for example. So that's called the sublimation curve. If I go this direction, that is sublimation. If I go this direction, that is a deposition, for example. Okay, fusion curve, same thing, going from solid to a liquid, right? So that would be melting, and liquid to back to a solid, fusion. Same thing with this vaporization curve, same idea. So the way we can read this, and then triple point. So like I said, that was a scenario in which kind of all three of those are occurring at the same time, essentially. And oftentimes this fusion curve will actually be the other direction. It'll be kind of up in this direction. So on that prior slide, it had mentioned that the freezing normally increases when you increase the pressure. This is a unique feature to water, and I'm sure other molecules as well, but water specifically, that's actually really important for its properties. This is one of the reasons why the solid is actually less dense than the liquid. So the solid floats in the winter, right? So you won't have lakes freezing from the bottom up. Obviously, that would be a huge problem, but there's lots of physical properties associated with water that are really important. And part of it's based on this fusion curve being angled to the left here instead of angled to the right, like almost all other molecules. Okay, so that's particular for water. You can kind of see at 0 degrees Celsius and 1 atmosphere, we know that is the normal melting point for water, and that's kind of why we see that phase transition right here. And then likewise, as we follow this along, if we're at 1 atmosphere, we hit the melting point, the boiling point at 100 degrees Celsius, which again is what we're familiar with. If we were to decrease the pressure, we would be boiling a little bit earlier, right? If you were to increase the pressure, you would be boiling much later and a much higher temperature. So that's what I talked about in that prior situation with pressure cookers or high elevation cooking, right? Where you'd actually have a lower temperature or a higher temperature for that liquid. So this is how you would read these phase diagrams. So here, let's do another example of this. So here we have CO2. phase diagram. So let's say we're going to heat solid CO2 initially at negative 100 degrees Celsius and 1 atmosphere, which is 0.1. So this is negative 100 degrees Celsius and 1 atmospheres. And we're going to heat it to the point and causing it to sublime when it reaches 0.2, which is at negative 78 degrees Celsius. So that's the sublimation process that we see all the time when you see dry ice, which is solid CO2. That's why you see it smoking. We're at 1 atmosphere. It's very, very cold. And if it gets as warm as negative 78 degrees Celsius, it'll start subliming, which of course room temperature, which is where we're seeing it at, is much, much higher than negative 78 degrees Celsius. So it's very, very cold. And that's why we see it subliming. We would have to be at much higher pressures in order to see it transition through liquid CO2 and then to vapor. So that's because of its location of this triple point. All right. Secondly, let's say do another situation. Let's say we're at 25 degrees Celsius, so room temperature, and we would like to get that vapor, that CO2 vapor, into a liquid, which CO2, of course, we're breathing it in right now. To get liquids, to get CO2 as a vapor at room temperature into a liquid, we're going to need to apply a lot of pressure to do that. So we would have to go up to about 70 atmospheres before we would start to see that CO2 vapor condensing into a liquid CO2. And liquid CO2 is used. There are scenarios where we use it. Liquid CO2 extraction is actually used for, it's used for lots of things, but one of them is taking caffeine out of coffee beans. So your decaf coffee actually uses liquid CO2 extraction to extract out that extract out caffeine from those coffee beans, for example. It's used for many, many other things, but that's kind of a common one. All right, so let's try some of these using the following phase diagram. Determine the normal boiling point and the normal melting point of the substance. So remember, normal boiling point, normal melting point was at 1 atmosphere. So here we can go at 1 atmosphere, head on across until we hit that phase transition. So we're going from a solid, which is this region, to a liquid, which is this region. Okay. And that looks to be maybe, 135 degrees Celsius melting point. Okay. Then we keep going. We're as a liquid right now. And then at some point, we're going to cross over into gas. So that's the boiling point. So maybe 200 degrees Celsius could be the boiling point for this particular compound, whatever it is. Okay, so that was kind of that first one. What about the second one? Determine the physical state of the substance at 2 atmospheres and 110 degrees Celsius. So here's 110 degrees Celsius. Go up to 2 atmospheres. This is clearly in the solid category. So this is solid up here at 110 degrees Celsius and 2 atmospheres. Okay, then lastly, let's determine the pressure and temperature that corresponds to the triple point of the substance. So we go down here to the triple point. And this looks like maybe 0.8 atmospheres and maybe 115 degrees Celsius. So this would be how you'd go about reading these phase diagrams.